No. Attendance is okay so far? Okay. We were almost finished with section 5.3. So we'll finish that and we'll start 5.4 today, and hopefully we'll finish it tomorrow. After today, look over the attendance and see if you have any questions and try the problems, and we can go over any that you want next class. There we go. We were talking about the umbrella problem and whether to carry your umbrella or not. And then, what is the logic status of the expected utility rule? It is certainly not math, because it's not based on math. It's based on your feelings or how much it may affect things, but it's not, you're giving it an estimate. It's not an actual value that you're finding. It's how you feel. And that's why it's a behavior of humans, how we would react, not just a mathematical object. There's 3 different ways of understanding the rule, or that you could look at it. Descriptive is a mental process. This is what's going on inside your head when we make a decision. Our brains are trying to find the best possible outcome as measured by expected value. For your final, your brain might be saying, should I study? Shouldn't I study? I know this much. I don't know this part. This is how much I should study. You're mentally processing it. There's no exact value of how much you should study. It's a mental process that you need to decide. Predictive as a model of human behavior. This may not be how our brains actually do work, but it is a useful way to model the decisions we end up taking. Many classical economists would take this point of view. Predictive, if I study this much, I predict I'll get a C. Or if I don't study, I know I'm going to get a D on the test, but with the points I have, it'll give me a C. So you're predicting what could happen depending on how much. Normative as a guide or an ethical principle. This is how we ought to make the decision, especially important ones. Or this is how a rational person makes decisions. And you don't want to be irrational, do you? Your teacher may say, and this is what they say, for every hour in a class, you should spend 2 hours outside of class. So this is a 4-credit class. So you should be spending at least 8 hours a week on it. That's the norm. That's what you're supposed to do. You may predict that you could do it in 6 hours, or you may have a mental process that goes through, and as long as I keep up with the attendance and the projects, I'll do as little hours as possible. So there's different ways for each problem to look at it each way. I'm not going to test on this part. It's just the thought process that goes through, kind of like whether you should bring an umbrella or not, how they found those percents. Okay, let's look at this problem. Your community is subject to repeated flooding from rainfall in a nearby mountains in any given year. The precipitation can be classified as low, medium, high, or exceptional, with the probabilities 27, 48, 24, and 1%, respectively. The corresponding annual amounts of damage due to flood is 21,000 for low, 260,000 for medium, 870,000 for high, and 4.6 million for extreme precipitation. The U.S. Army Corps of Engineers proposes to build a dam to protect your community. The construction of the dam will be financed by a bond issue. Repayments on the bond will cost $100,000 annually. The dam will reduce the flood damage 0 for low, medium, and high precipitation amounts. However, an extreme precipitation event occurs, a 100-year flood, the dam will burst and the total amount will be 25 million. Should the community build the dam? Make a payoff matrix. C is the annual cost to your community in thousands of dollars. So we're going to put it in thousands. That way we don't have as many zeros in our table. First is the probability. So you would put each probability. Now, when you're multiplying, you need it as a decimal. So it's up to you if you want to put the percent and then change it. Low, medium, high. So it's going in order. Low precipitation is 27%, or you could put 0.27 because that's what you'll have to multiply with. Medium, 48%. 24%. And 1%. Cost to the dam. Corresponding annual amount of damage. So in low, it's 21. Remember, it's in thousands, so it'll just be 21. 260,000 would be 260. 870,000 would be 870. Now we have, there we go, 4.6 million. A 1,000 was 3 zeros. 4.6 million would be this. We're dividing 1,000. So we're getting rid of 3 zeros. This would be 4,600. Because it's in thousands. So the cost if there's no dam would be low precipitation 21,000, medium 260,000, high 870,000, and then this would be 4,600,000. Any questions on that part? Now, if we put the dam, see, this didn't include the price of the dam because this first one is if we don't build it. But in the second one, it's the cost with the dam. So if we're building the dam, it was 100,000. Taking out 1,000, it's 100. We took out 1,000 because it's in thousands. So the cost is $100 plus damages. But notice it says dam will reduce the flood damage to 0 for low, medium, and high. So these three, there's no extra cost, just building the dam, which is 100,000. The high precipitation is 25 million. plus the cost to build the dam. Any questions so far? So I took the damages if the dam is built, plus the cost of the dam, and then we're going to take 1,000 out. Oops, I lost the one. Any questions on setting up the table? Seems like only 1%, but it can happen. In Houston, where my cousins live, there's a dam, and one of the storms, the dam was going to burst. But instead of letting it burst, which they're talking about here, they opened the dam and let out enough water so the dam wouldn't break. But then the community behind it, underneath it, was wiped out. But it was cheaper to let all of those homes go than it was to allow the dam to burst. So even though they're building the dam and the dam could get damaged, chances are they're going to open up the dam and everything below all the homes will be flooded. So those who are living below still need to pay for flood insurance and things like that, because this 1%, it still can happen, especially with the storms we've been having lately. Anything is possible. So they say 1%, but it could get bad enough that they just open the dam and it still causes the damage. Okay. So we want to find the expected value. Remember, C is the annual cost. And they want the annual cost if there's no dam. So that would be this row here, the middle one. That's the one with no dam. Expected value, you take your cost times your probability to find the expected value. So with the no dam, it would be 21 times 0.27 plus 260 times 0.48 plus 870 times 0.24. And the last one, 4,600 times 0.01. And that will give you the expected value. Getting 385. Now remember, that's in thousands. They just did 385 though. Oh, it's the whole community. I was going to say that can't be per person. Any questions? So when you're finding the expected value, it's each outcome by its probability. So then if we want to find the expected value for the cost, if they put a dam, you take your percent times the bottom row. Writing up a hill. Are we getting 350,000? So build or not build? If we just go by the expected value, if we have a dam, there's less cost to the community by 25,000. So this one would save the community $25,000 a year. If we just look expected value, we would build. But remember this 1%, if with the dam, 25.1 million. Where this is only 4.6 million. And the chances of one of these happening is only 1%. So if it's that unlikely, although notice with these storms, we're saving money here. 160,000, 770,000. But if you take several years and then average it, this one's better. Any questions on that? But if we just look at expected value, we're better off building the dam. Any questions? Now, think about if you live downstream, you might well be a bit queasy about this recommendation. I mean, like I had said, putting up the dam doesn't mean that it won't get high and they won't release the water. Those expected values of C are quite close after all. And whereas you expected losses without the dam are made up of many small, moderate-sized events. The event of losses with the dam dominated by the chance, albeit tiny, a huge catastrophe could happen. And I know it's happened a lot where my cousins live, at least 3 different times they've had to open the dam in the last maybe 10 years. So that's, I don't know that 1% is accurate, but maybe for that community it is. Is that a gamble you think you want to take? If you don't want to take that chance, you might be exhibiting risk aversion. A person making a choice to place risk aversion if they prefer greater certainty in the outcome, even at some cost to their expected payoff. So it means that even if there's a little chance of making it bigger, you'd rather not take the risk and keep the secure, kind of like stocks. You can put your money into a savings account and it's safe, but maybe it's only making 2%. Right now, though, bonds or CDs, not bonds, CDs are making 5%, which they haven't made that in a long time if you wanted to open a CD. But say the savings account's making 2%, and you could put it into stock making 10%, but that's at a high risk. Do you want your money only making 2%, but you know it's going to be there tomorrow? Or do you want to take that risk and go put money in a couple different ones? So if one goes, you still have some, but you still could be at a loss. That's risk aversion. The risk aversion person takes the safe one. I know if I have 10,000 and it's in a savings account, it's going to be there every single day. If I put it into stock, it could be gone the next day. I would not take my chances. I don't care what the percentage is. I just don't have money I can take that chance on. When my daughter was little, she had gotten $2,000 for baptism. I put that into a stock at a bank because they were going up really quick and splitting. But then as soon as it split and it was high, I took it all out because I didn't want to risk losing it. Because after you see what's happening to all these other ones, it's like, I want to be safe. But it did double her money, but then I pulled it out. And this is another example of that. What would you prefer? A guarantee of receiving $50, so you could get $50, or they say, if you flip a coin and it lands heads, I'll give you $100. If it's on tails, you get nothing. And that's the thing. Is it worth the risk to try and get that 100, or stay safe and know you got 50? And that's what risk aversion is. Risk aversion person would take the 50. They don't want to risk it. They want greater certainty. Any questions on that? That's everything in that section. In the year 2012, there were 53 unprovoked shark attacks on swimmers in the US. US population that year was 312 million. So we could estimate that the probability of a random person in the US being attacked by a shark would be 53 out of the 312 million. And what they did was they rewrote it into scientific notation. 3678, 3.12 times 10 to the 8. When you divide these two numbers, you'll get this. Remember that negative 0.123451 6. So it's a very small chance. And this is the rate. If you made it a percent, you'd multiply by 100. Now, you didn't have to write it all the way out like this. You could leave this. You can tell -7 is going to make that really small. So that's the probability that any person in the United States will get attacked by a shark. That's not very accurate, though. Why is it wrong? I mean, they're including everybody in the United States. But what if everybody in the United States didn't go swimming in areas where there's sharks? A lot of this is people who aren't going swimming. So to really be able to tell, you'd want to find those who go swimming in shark areas, what the probability of being attacked would be, not all Americans. And so if you're one of the ones who don't go swimming or aren't near there, so it's not very likely that you do, this doesn't have any meaning. So it shouldn't include everybody. It should only include those who went swimming, at least that year. So then you have an average of how many people go swimming each year. So like our judgment of probability that you will be attacked by a shark, risk judgments in sustainability science are regularly updated with new information. this wasn't very accurate, plus the population keeps changing. And so these need to keep being updated. Anytime you're looking for information for a class and you want statistics on it, make sure you look at the years. You don't want something from 2000 when it's 2023. Those 23 years, things could have changed a lot. Now, I'm not saying you shouldn't look at it. Maybe you'll find things that, wow, I'd like this in a newer amount. And then you go looking for it. Or some things don't change. Algebra is still algebra. It's been the same. But there's been new ways of learning things. So you do want to make sure, because it keeps changing, that you're getting the newest information. The language that mathematicians use to describe this updating process is conditional probability. And we've talked a little bit about this in the last section. The conditional probability is when one part is given. And I showed you this formula earlier, and now we'll use it. Conditional probability is an event is the probability after some new piece of information is taken into account. A conditional probability is written like this. Probability A given B. So the given part is the second part. It reads probability of A given B. This means that the probability that A occurs if we already know B occurred. There's a few ways to find it. We'll look at a formula that we used in the last section and a few other ways. But the second part is the given. Now remember also this intersection is and, so it's the probability of A and B divided by the probability of B. One way of finding it without using the formula is a Venn diagram. So if we look at this example, consider the rolls of a fair die. Let A be the event we roll an even number, and B be the event we roll 1, 2, 3, or 5. Draw a Venn diagram, list the set sample spaces. Let's list the sample space first. I think that will help. Oops. A, rolling a die, is the even. Sample space, when we roll a fair die, one fair die, 1 through 6. So sample spaces are just listing, and this is the entire possibilities. If we roll a fair die, we can get the numbers 1 through 6. A is the even, so 2, 4, 6. B is 1, 2, 3, and 5. So if we drew a Venn diagram, and notice they do have a 2 overlaps. So they will overlap. So we said the 2 overlapped. It's the only one that is in both of these. So that means in A, we have 2, 4, and 6. In B, we have 2, 1, 3, 5. And 1, 2, 3, 4, 5, 6. We have all of the sample space. If one of these wasn't, say the 5 wasn't in there, then we'd have to include it out here. But A and B combined is the whole sample space. Any questions on setting that up?
So if a number is outside. We put it outside the Venn diagram.
If there, so say the 5 wasn't here, then it would go outside the 2 circles, but it would still be in the square. So if there was something in the sample space that wasn't included in A and B, then it would go outside of A and B. So if we took that 5 out, it would go out here. I'm going to put it back since it was included. But, does that answer your question? It would go with
Yeah.
the S. Okay.
Okay.
So anything from here that is not in these two has to go out here. But in this case, if we take A union B, that would be a 1, 2, 3, 4, 5, and 6. If A union B is equal to your sample space, there won't be any extras. Remember, union, it takes one of everything. When you have a repeat, you don't write it twice, but it takes everything and puts it together. If it includes your sample space, then there will not be anything out here. We can make another one and we'll do it with one out here. Now, if we do the probability of A given B, if we know that B is going to happen, that's this one here, then we know it's not going to be 4 or 6. If we know B is going to happen, then we know the 4 and 6 is out. So the probability of A is 1 out of 4. So the Venn diagram says we know it's going to be B. That takes this part out. It's only B. And to have A happen is 1 out of the 4. Any questions so far? The probability of B given A, this time we know A, so that gets rid of this, because it has to be an A. The probability it comes from B then is 1/3. Any questions on that? Okay, let's try doing it using the formula. So the probability of A given B equals the probability A and B divided by the probability of B. A intersect B. Intersection, it's right in the middle here. So the probability of A intersect B is 1 out of the 6. The probability of B is all 4 of these, 4 out of the 6. Now, when you're dividing, you can flip the bottom one and multiply. The 6's cancel and leave 1/4. It's just another way of doing it. I think if you can write it all in a Venn diagram, it's easier. Sometimes that's not always the case. You may not know all the numbers, just the probabilities. If you were going to put this into a calculator and got the decimal, you'd want to put the top and bottom in parentheses. And then you should get 1/4 is a quarter, 0.25. Okay, go ahead and try the second one. Probability of B given A is the probability of B and A divided by the probability of A. And when you reduce, you should get 1/3. Probability in A and B we found is 1/6. The probability of A, there's 3 of them. 3/6. 1/6 times 6/3. When you're dividing by a fraction, you can flip and multiply. Probability is the same. Any questions on that? Another way is a frequency table. So we're using the same values, whether we look here, here, or what they wrote up here. Now, what they do is they put one part going across and the other part going down. So across is that B occurs and B does not occur, and going down is A's. So this first box means that both of them occur. And we're just putting how many. Not, you could use probabilities, but in this section, they were just counting them. So if we count them, A and B, there's only one way for A and B. If it's a 2, then it's A and B occurs. So there's one way. B occurs, but A does not. So for B occur, it's this. And then not A takes this out, so there's 3 of them. Notice adding across, you get the 4 that are in B. B does not occur, but A does. So if B does not occur, that gets rid of all of this. And A is occurring, so that's 2. So for A to occur but not B, that takes all of B out. There's 2 of them. Go ahead and try the next one. B does not occur and A does not occur. If B and A do not occur, are there any other values left in our sample space? So that would be the case if there was a number out here. If the 5 wasn't in there, then there would have been one where both of them don't occur. But in this case, they cover the whole sample space. So there would be none. Adding across. So if B occurs, there's 4 possibilities. If B does not occur, there's 2, which makes sense. We have 4 inside B, 2 that are not. And when we add down, we have our 6. If we add down here, because total 3 and 3 is 6. So adding down and going across needs to match, or you did something wrong. Any questions on setting it up? When we're finding the probabilities using the table, we look at the first one, the probability of A given B. This means that B is occurring. If we know that B is occurring, then we're just going to use that column. We're not going to use the rest. We're only going to use this. Because we know B happens. What's the probability A happens? 1 out of the 4. We're not using all of them because we know B occurs, so you only use that row. So it's 1/4. The probability of B given A, notice we know A is occurring. A occurring is a column. So now we're only using that column. We know A occurs. What's the probability that B occurs? 1 out of the 3. The same answers that we got here. 1/4, 1/3. So it's 3 different ways of solving the same problem. It depends on what other information you want to show. Here, we don't know what the values were. We know there's 1 for both of them. 3 where it's B but not A. So we know information, but we don't know the numbers, depending on what you need. The Venn diagram, you have all the numbers. And probably if you're using this, all you have is the percents. So it's just 3 different ways of showing your information. And if you're given information, how to find things from it. Any questions so far? What else did I ask for? Probability A and B. So if one of these are at random, the probability of A and B, A and B, that means B occurs and A occurs. There's only 1 out of the 6. Now, what you have to remember with an OR, and we were given this formula in a different section, it's the probability of A plus the probability of B, but you have to subtract their intersection because they overlap. If we did the probability of A going down, that's 3. And then the probability of B would go this way. Notice we're using this twice. 1 plus 3, there's 4 out of the 6. So when we went down, we added the 1 in. When we went across, we added it in. That's why we have to subtract it out. Remember the probability of A or B, that would be everything being combined or a union. So or is union. And is intersection. So we could put or we could put union, we could put and, or we could put intersect. Any questions on that? Did you need to see another one where the sample space? Yeah, let's do one real quick. Just so you could see the Venn diagram. And we'll roll a die. So the sample space is 1 through 6. A will be 1, 3, and 5. And B will be 2, 3. Yeah, we'll just do that. So if we want to draw a Venn diagram, the first thing you want to do is see where they intersect, because then you want to make sure you put them in the center and not out here. Notice the 3s are where what they have in common. So the 3 is the overlap. And then A, besides 3, has a 1 and a 5. B, besides the 3, has a 2. If we look at our sample space, 1, 2, 3, we're missing a 4 and a 6. Any questions on that? So if we wanted to do the probability of A given B, we know it's in B, so that takes out this and this. To be in A, it's 1/2. The probability of B given A, go ahead and try that. So we know it's given A, so that takes this out. The probability it's B then is only that 3, so 1 out of the 3. Any questions? Okay, if you do not have any questions, I will see you tomorrow.